let's talk about error propagation. So here's an example. Suppose we measure the side of a square to be 5 meters with an error of at most 4%. How much error will there be in measuring the area, and what percentage error in measuring the area will there be? So the calculations actually are not too terrible, but it's kind of nice to see a picture of what's happening. So here's my square, and it's got a side length of 5 meters. And well, it actually could be 5 meters. Sorry, is there, do you want me to clarify anything? I see you guys are like trying to read this a little bit here. Let me zoom in a little so you can see a little bit better. And writing is not always 100% excellent. But it really could be between. So how small could the side actually be if you have a 4% error? Well, 4% of 5 is going to be 0.2 meters. So it could actually really be between 4.8 meters and 5.2 meters. That could actually be how small or big the side is. So the small square could be, I'm just going to make a small square here. Thanks. Now the issue is we don't actually want to calculate the area of these squares, right? You don't want to do 5.2 squared or 4.8 squared. We could, and here's what I kind of like to think about. And here's kind of the picture that actually helps. So let's draw the bigger picture because that one's easier to do. If I increase this by 4%, if I increase the edge by 4% to be 5.2 meters, well, the amount I'm increasing it by is 0.2 meters. Sorry, that's it. Thanks.
Thank you.
And so how much area is in this rectangle here? Well, it's 0.2 meters times the 5 meters of width. That's actually going to be exactly 1 meter. That rectangle there has 1 meter of area, 1 square meter of area. This rectangle there also has 1 square meter of area. And this rectangle here is 0.2 times 0.2, which is going to be 0.04 meters. So we could actually find the area of this by adding those together. It's going to be 25 plus 1 plus 1 plus 0.04. It's 27.04 square meters. Okay, that's not the point though. The point is that we're trying to approximate how much we're going to be off by, right? We don't want to do this calculation every time. It's kind of annoying. So what we do instead is we say, well, we know that the area equation is going to be x squared. And instead of counting or instead of calculating the change in area, we're going to approximate the change in area. So instead of calculating delta A, we're going to say that's approximately the differential dA. And really, when I'm thinking about the differential dA, I'm thinking of it as the derivative times the change in x. What's my derivative? 2x. And what's the differential? What's the change in x for this particular example? Well, in this case, it's 0.2, because that's how much off we could be by, which is 4% of 5. Okay, well, now look at this. If I plug in the measurement for x, which was x equal to 5 meters, look what we're getting. We're getting that the change in area is approximately 2 times 5 times 0.2, which is 10 times 0.2, which is 2 square meters. what I really, really, really want you to see is that that's the areas of those rectangles there. Not the black one, the two red ones. So when you increase the area or the length of a square, you're kind of, if you're approximating that increase, you're kind of saying, well, I'm going to approximate it by these red ones, and I'm not going to worry about the small one in the corner there because it doesn't actually count for that much. So that's how our approximation is actually working here. Now, the way I wouldn't actually draw this if I was doing this problem, right? I would do this work. I say, okay, well, the area is x squared. The differential is an approximation of how much we're off by, and that's going to be dA, which is the derivative times dx, and then we're just plugging values in here. Now, how much area will we be measuring here? I could be a little more specific, and I should probably say that the absolute value in the change in area is less than or equal to 2 square meters. Because maybe it got bigger, maybe it got smaller. So we typically use absolute values when we're talking about error propagation because we're not really sure if it's bigger or smaller. Now, the other interesting question here is what's our percentage error in measuring the area? Well, the interesting thing about that question is you don't actually need to know what you measured the side length to be. We're going to use it first, but then I'm going to show you again how we don't need that. So percentage error, using the numbers we've got, well, the error in absolute value is less than or equal to 2 square meters. And the percentage error, sorry, you guys can't see that, apologize. The percentage error is less than or equal to 2 square meters divided by the total area, which is going to be how much? 25 square meters. Then we usually like multiply by 100 to make it a percent. 2 over 25 here is going to be 8 over 100, which is 0.08 or 8%. And which is all fine if you have numbers. But I want to do this without the numbers because someone might ask you a question like, we measure the side length of an area accurate to, side length of a square accurate to within what, 4%. How accurate is our measurement of the area? What percentage accuracy are we at? And you don't actually need to know what you measured the side length of the square to be. So how do we do this without numbers? Well, the area of the square is x squared. And we know that our delta x, I should say not really delta x, our delta x over x, that is the percent error in our measurement. That's going to be less than or equal to 4%. We're going to go back to our differential and say, well, okay, the error in A is approximately the differential of A, which is dA dx times dx. The dA dx is the derivative. That's your x squared. And your dx is going to be, well, this is where things get interesting. I'm going to replace dx with delta x. Sorry, apologies here. That's not x squared, that's 2x. Sorry about that. And that's our error. But now I want the percentage error in area. That's going to be your delta A divided by A. Thank you. Which is approximately going to be this here, your 2x times delta x divided by your area, which is x squared. And look what happens. You can cancel an x there, and we've got 2 times delta x over x. Well, if we put absolute values on everything, like we should, we know that delta x over x in absolute value is less than or equal to 0.04, 4%. This is less than or equal to 2 times 0.04, which is 0.08%. So you don't actually need to know what X was measured to be in the first place to find out how much percentage error there is in the area measurement. And this is true kind of for whatever, well, really you can do it for any function, but it's especially true for nice functions where we're talking about area or volume. So let's look at a volume example and we'll kind of see a similar thing happen. I mean, I should actually pause. Let me pause and see. Do you guys have any questions? Super straightforward. Everyone's like 100% I got it. No worries. All right. If that's the case, let me ask you a question. I was like, oh no. Let's say we measure the radius of a sphere accurately to within a 5% tolerance. How accurate, or I should say within what tolerance, percentage error, will our measurement of the volume be? And here's where I would, so I'm going to let you guys work on this for a minute, but here's where I would start. You're trying to calculate this. You're trying to figure out what delta V over V is. And we're going to approximate that with dV over V. And in case you forgot, the volume of a sphere is given by 4/3 pi r cubed. So try working on that for a moment. You're going to need to use the fact that the percentage error of the radius is 5%. So we have that delta R over R in absolute value is less than or equal to 0.05. Oh, thanks, man. Everyone at home should work on this too. Or wherever you are. You might not be at home, might be somewhere else. What's going in for dV? You could also use dr, but yeah, kind of use interchangeably. And actually, I should kind of make that extra super clear. when we're doing this sort of approximation thing, we're saying that the change in the function is approximated by the differential dv, but the change in the independent variable r in this case is not approximated. It is actually what we're calling delta r. So dr and delta r are actually literally interchangeable, just like in the previous problem. Dx and delta x are actually interchangeable because we're just talking about the change in x, whereas dA is an approximation of the actual change in area delta A. So the function is being approximated, or the change is being approximated, whereas the input variable, its change is exact. So here, dv is the derivative of the volume function, which is 4 pi r squared times dr, or delta r if you prefer. And then stuff cancels. A 4 cancels. A pi cancels. And r squared cancels. And we're left with dr, or delta r, over 1/3. Oh, well, I don't want that fraction in the denominator. I'm going to bring that out as a 3 times delta r over r, which we know delta r over r is less than or equal to 0.05. So this is going to be less than or equal to 3 times 0.05, which is 15% of 0.15. There's kind of an interesting truth about at least objects with dimensionality. So if you're measuring something and you're asking what percentage error there could be in something that has like 3 times as much dimension, the answer is 3 times as much error. So it's kind of interesting, right? In this previous problem, we measured the edge length with 4% error, and the area, which has twice as much dimension, had twice as much error. Sorry, I can't see what I'm pointing to. That's not a coincidence. Same thing is happening here. The radius having dimension 1 and the volume having dimension 3, right? The error is 3 times as much. And if you find the surface area here, right, the percentage error in the surface area would be, well, it's going to be the change in the surface area divided by the surface area. That's going to be approximately the change, the differential ds divided by s. The surface area equation is 4 pi r squared. And the derivative of that is 8 pi r times dr for the differential. And look, the pi's cancel, 8 over 4 is 2, and r cancels, and we exactly get 2 times dr over r, or 2 times delta r over r, which in this case is going to be 2 times 0.05. I should say less than or equal to 2 times 0.05, which is 0.10, or 10%. Kind of neat. It's less applicable for when you're just given like a function. So let's do another example. But before I move on to another example, I should begin. Are there questions? Yeah. Surface area. So yeah, this is the surface area. And spheres are interesting in that the derivative of the volume of a sphere is equal to the surface area of a sphere. And that's kind of a unique trait. It's also kind of true for circles, right? The derivative of the area of a circle is equal to the circumference of a circle. But it's not true for other shapes, right? The derivative of the area of a square is 2x, but the perimeter of a square is 4x. Or the derivative of the volume of a cube is 3x squared, and the actual surface area of the cube is 6x squared. So don't get caught up thinking that that always works. It only works for spheres and circles. Oh, I had one other one over here. I had one more. Yeah, here we go. Let's look at this one here. I'm always kind of surprised when they talk about cone stuff, because surface area of the cone always feels That was always the formula I told students, you never need to know the surface area of a cone. No one's ever going to ask about that. It's crazy. And then, of course, it's popping up. So surface area of a cone. So I should point out that the lateral surface area of a cone. You can see that? Of course not. Why would I write in the right place? Is given by the formula surface area is equal to pi times r times the square root of r squared plus h squared. Now, if you've looked up the formula for surface area of a cone on the internet, which I imagine many of you have because it was the homework question, there's another piece, right? There's a plus a pi r squared because that's the part that's the area of the circle on top that we're not talking about. So the usual formula you see is usually written kind of terribly as pi times r times r plus the square root of r squared plus h squared. Because that part there is the circle on top, and that part there is the around part of the cone. And that's what we're looking at here, the lateral surface area, not the top part. Okay, and the question we're going to ask is, use a differential to approximate the change in surface area that results if the radius of a cone, of height 4 inches increases from 3 to 3.3 inches. Okay. So a couple things to be aware of here. The height isn't changing. Height is staying the same, 4 inches. The radius is increasing from 3 to 3.3 inches. So we're trying to find the change in surface area. And we're going to approximate that with the differential, which is going to be the derivative times. So now we have to be a little bit careful because this is a function of two variables. But really it's not. Because in this setup, in this setup, we're saying that the height is staying constant. So really, I should actually take a moment and say, oh, my surface area equation for this particular problem is pi times r times the square root of r squared plus 16. Because height is 4, and 4 squared is 16. So then this differential is really going to be s prime of r, the derivative as a function of r, times dr, or delta r. So that's what we're figuring out here. All right, this is going to get a little bit messy because our derivative is going to require the product rule. Oh well, that's life. Sometimes that happens. So I would probably re-express this as pi times r squared plus 16 to the 1/2 power. Make it a little easier to differentiate. So ds is going to equal the derivative of that. Okay, I've got a pi. And then the derivative of that's going to be 1 times r squared plus 16 to the 1/2 plus r times the derivative of that, which is 1/2 times r squared plus 16 to the negative 1/2 times the derivative of the stuff inside, which is 2r, times dr, or delta r. This is a good example of don't simplify if you don't have to. We still need to figure out what the answer is, but this is an excellent. So this problem was kind of set up very specifically. My r is 3, and 3 squared plus 16 is 25, which is going to be nice to take the square root of. So this is where we should definitely just plug in r equal to 3 and delta r equal to what? What is our delta r? 0.3, yeah, 0.3. So if we plug those in, we're going to get that the actual change, which is approximately the differential, is pi times, all right, 3 squared is 9 plus 16 to the 1/2 power. If we cancel a 1/2 and a 2 here, and r times r is r squared times 9 plus 16 to the negative 1/2, all times 0.3. So again, to kind of think about what we're doing here, this part here represents kind of the slope, right? You're saying, okay, if you increase r by so much, this is what you're going to multiply it by to figure out how much you increase the surface area by. Right? Because the r is the independent variable and the surface area is the dependent variable. So if we're changing r, we're asking how much change in s do you get? And we're figuring that out by taking your change in r and multiplying it by the slope to get your change in s. So what have I got here? I've got pi times the square root of 25 is 5. And this is 1 over the square root of 25. So 1 over 5. So I got 9 over 5 times 0.3. Okay. So this is 25 over 5 plus 9. That's going to be pi times 34 over 5. I feel like decimals might be better here. We could probably make that a much nicer, right? Because 9 over 5 is just 1.8. So I could have this being, I don't know. Either way, I would probably make this, I don't know, 1.8 plus 5 is 6.8 times 0.3. That feels like a calculator kind of thing to do. So I would get a calculator. 0.3 times 6.8. Just 2.04. So this is equal to 2.04 pi. Which you could then approximate further if you wanted to. Now, no, I don't think so. All right, let's look at a slightly different version of this. Actually, so questions, comments. I feel like there's always questions about this. I want to give you the chance. I just want to move on and feel like everyone got it for sure. Things I could say more clearly. Pretty clear. So, just as a reminder, if you're finding the change in a function, you're going to be finding delta f. Gosh, every time. I guess I could zoom back out a little bit. You're going to be finding delta f and approximating that by df, which is just the derivative times dx, or the derivative times delta x. And then the percentage change in f is going to be delta f over f. Usually in an absolute value, because typically it can go either way, which then ends up being approximated by df over f. And then that's going to be the same kind of thing we got up here. The derivative of the function times delta x over the function. And if it's a nice volume or area thing, then stuff cancels nicely. Right? Just as another example, if your function was, say, if your function is the function for the volume of a cube, then f of x is x cubed, and f prime of x is 3x squared. And so this stuff happens to simplify really nicely. This percentage change in error gives me that delta f over f, which is approximately df over f, is, well, my df is 3x squared times delta x. And my f of x is x cubed And things work out real nice. That's just 3 times delta x over x. And you have to kind of use the fact that, oh yeah, the delta x over x, that's the percentage change in your input. So when they're giving you percentage change and you're asked about percentage change, it's easy to just kind of do it that way if you're talking about shapes with volume or area. When it's other functions, it's a little less nice. There's something else I want to point out. Oh yeah, I should point out my formula here is missing the times 100 because I didn't want to write it. So my percentages are as decimals here. If you need to write it as a percentage, I think you know how to make that change. Well, let's say we had something like this. Let's say our function, well, I should say, we measure x, the input, to be 6 accurate to within 2%. And then, actually, say the right words here. The value of f of x is given by, let's say, 10 over 4 plus x. And we want to know 2 things. We want to approximate the possible error in f of x. We want to find delta f and also the percentage error. Which is delta f. And the problem with a problem like this is that you can't kind of do the nice slick thing we did before. What I would really love to be able to do here is say, okay, well, I know if I was just trying to do the second part, I would love to be able to say, I know that delta x over x is less than or equal to 0.02. Question, concern? Which part? Sure. Approximate the possible error in f of x, which I've written as the absolute value of delta f, and also the percentage error. Sorry, I know. Sometimes the writing is. Don't hesitate to ask me to clarify something. I'm not. I have no illusions about the fact that my writing is not excellent looking. So it'd be really nice if we could say, well, I'm going to take delta f over f and make this pop out of it. Sometimes that's possible. I don't think it is here, although let's take a look just to be sure. So that's going to be approximately df over f. And let's find the derivative real quick. So if f of x is 10 times 4 plus x to the negative first, f prime of x is going to be negative 10 times 4 plus x to the negative second. This might work out. I don't know. Let's see. It might not. So if I'm going to write df, that's going to be the derivative times your delta x over your original function. And if you're looking at this and thinking it looks terrible, you're right. I don't see a way we're going to get this showing up. Right? I don't see a delta x over x coming out of this mess. I can cancel some stuff, but that's not really going to help me. If you simplify this, it ends up being delta x over 4 plus x. I drop the negative sign because the absolute value would take care of that. But that's not exactly what I wanted, right? So we're kind of stuck actually using the numbers here. So this was maybe worth looking at, but maybe not. I will, again, circle back and say this idea of trying to talk about the percentage error in terms of the percentage error of X does work if you're talking about geometric formulas. So if you're talking about area or volume, when you're given the input kind of, it definitely is simple to do this kind of thing. Well, I should say not simple. It's possible to do this kind of thing. It can still be a little challenging. So let's go ahead and actually do the problem like we're supposed to do it. So the value of f of x is given by 10 over 4 plus x, and we have been given that x is measured to be 6, accurate to within 2%. Okay, so I'm trying to find the change in f, which is approximately df, which is going to be this top part here. It's going to be this negative 10 times 4 plus x to the negative second times your delta x. And we can just plug in what delta x and x are. That's going to be negative 10. That's the value. Times, let's see, x is 6. So we got 4 plus 6 to the negative second. What's delta x? That's a good question. What is delta x? They didn't tell us. They told us that we measured x to be 6, accurate to within 2%. So how much change in x could there be? If you guys say 2%, I'll be like, okay, fine, that's true. But how much actual change in the value of x could there be? Well, there could be 2% of 6, which is going to be what? 0.12? Yeah. So that's what our delta x is. It's 0.12. I suppose I should really say that's what our delta x is less than or equal to. I wouldn't sweat too much worrying about the less than or equal to signs here, but technically, right, when you were saying delta x is at most 1.2, it could be smaller. And then we would calculate this. That's going to be 10 divided by 10 squared times 0.12. I dropped the negative sign because, again, absolute values. And then that's going to be 0.12 over 10, which is 0.012. So that's our approximate change in the function f. And then if we want to find the percentage change, we would take that and divide it by the function value. Now, this one happens to be the same because the function value was 1. So percentage change in f, which is this delta f over f, is this value we just found divided by f of 6. But f of 6, if you look at the function, f of 6 is just 1. So the percentage change is about 1.2%. These ones where they're just giving you kind of a random function and asking you these things feel more arbitrary to me. It's like, okay, you have an error measurement in x, and then there's this function that depends on x, and you're asking how much that function could change. It seems a little weird. Whereas with the shapes, like, okay, we're measuring the shape to have a certain value for its thing, and then if you change that by how much are you changing the volume or the surface area of the shape, seems like a more easy to visualize type of question. That's all I really have to say about error propagation. We have 9-ish minutes left. Is there anything you would like me to say? Yeah. Totally, yeah. So this is so error propagation is under the guise of linear approximation, but linear approximation, sure. So typically, if I was asking a student a question, I would ask them to approximate. There's a bunch of different things I can ask. I could say approximate the square root of 35 or the cube root of 127 or something like 2.003 to the 4th or the natural log of 1.07. These are all good examples of things that you should be able to do an approximation of using a linearization. So we'll do one of them, but what I want to do first is actually show you for each of them kind of what you would do. So for this one here, our function would be the square root of x. We'd find the derivative. And more importantly, we'd find the a value. What's the value of a that's close to 35? It's easy to plug into the function. 36. All right, for this next one here, don't worry, we'll actually do some of these. My function is what? Right, you're just taking the function, the thing you're asked to approximate, and replacing the numerical value with x. Our derivative here is 1/3 x to the -2/3. And the value of a that we're going to pick that's close to 127 is exactly. If you don't know it, the easy way to figure it out is, well, like, okay, I know 4 cubed is 64, 5 cubed is 125, and 6 cubed is going to be way too big to be close to 127. So it's definitely 125. For that one there, our function is x to the 4th. The derivative is 4x cubed, and the a value is 2. Right? 2 is the easy number to plug in. And for the natural log of 1.07, our function is the natural log of x. The derivative is 1/x. And what's the a value there? 1. So that's the idea for each of these. The important part really is identifying what the function is and being able to take its derivative, and then what the a value is that you're going to plug in that's easy to evaluate. After that, the linearization, well, we need to remember the formula. The linearization of x is f of a plus f prime of a times x minus a. So if I wanted to approximate the square root of 35, sorry. So for the square root of 35, I would use the linearization of this function square root of x at this point 36. So it would be L of x would be f of a, so that's going to be the square root of 36 plus f prime of a, which is 1/2 root 36 times x minus a, which is x minus 36. Oops, sorry. That is my linearization. Should I simplify it? Well, I should be more specific. I should definitely simplify these values. So my linearization here is 6 plus 1/12 times x minus 36. Should I simplify that any further? Not really. I don't actually, no, I really don't want to. I really don't think you want to, is actually what I'm trying to say. So if I'm going to find the linearization at 35, and I think this next thing I'm going to write is kind of nice to write. I'm going to write that the square root of 35 is approximately the linearization at 35. I think it's nice to say that, because what we're really saying here is that the square root of x is approximately the straight line L of x. And so then we're just saying, oh, I wanted to approximate the square root of 35. I'm going to plug in 35 for x. And I'm going to get 6 plus 1/12 times 35 minus 36, which is just 6 minus 1/12. If I was short on time on a test, I would stop there. If I had all the time in the world, like I'd done anything else, I could come back, I would probably, well, it doesn't really come out to be a nice decimal. I would write it as a fraction, meaning I would say that's, well, I don't know, if your teacher is cool with mixed fractions, I guess you could say it's 5 and 11/12. Most of the time, in my experience, teachers have not been super cool with mixed fractions. Instead, you should write it as an improper fraction, meaning 72/12 minus 1/12, which is 71/12. How much time? Yeah, we got time. We can do another one. Which other one should we do? Let's do the natural log of 1.07. So there, it's still the same formula, right? Our linearization is still f of a plus f prime of a times x minus a. It's just in this case, our function was natural log of x, so our f of a, right? Our linearization is going to be f of a, which is natural log of 1, plus f prime of a, which is 1 over 1, times x minus a, which is x minus 1. The natural log of x1 linearized at x equal to 1 is always feels kind of boring at the end, because if we do simplify this, which I do think we should in this case, natural log of 1 is 0, and 1 times that is just x minus 1. So the natural log function near 1 is linearized by the graph y equals x minus 1. Which, if you think about the graphs, makes sense. Here's the graph of the natural log of x at the point 1, 0, and the graph y equals x minus 1, right, does that. I'm sorry. You guys really should tell me if you can't see it. I mean, I will move eventually, but if you let me know, they're like, oh yeah. So if I want to approximate the natural log of 1.07, it's going to be the linearization at 1.07, which is just 1.07 minus 1. 0.07. So this is the process for approximating something. Find the function, and the function usually is just take the expression and replace the number they're inputting into it with x, find the derivative, and then think about what the a value needs to be. And after that, you just have to toss it all into this formula and then plug in the x value that you're actually trying to approximate the function at.